Welcome back to My Favorite Universe. Today, we're going to tackle a pretty hot topic, and that's the one that involves the search for planets in our galaxy. Now, the search for planets takes on many dimensions. You might think, well, why search at all? We're pretty sure the galaxy, the Milky Way galaxy, our galaxy, has planets in it because the Sun's got 8 or 9 planets. Before the 1990s, our 8 or 9 planets were the only known planets in the galaxy. Right now, we happen to be rising through 100 planets known outside of the bounds of the solar system. And that number of planets were not discovered just because people were curious whether there were planets elsewhere in the galaxy. I always had the confidence that if we looked, we'd find them. No problem there. What's really going on here is that we're trying to find worlds that could support life. And if the Sun is an ordinary star, not too bright, not too dim, not too hot, not too cold, not too massive, it's ordinary. And it's got all these planets, and one of them has life on it. Then imagine other ordinary stars in the galaxy. So it becomes an exercise of not just simply filling catalogs of planets, as we've done before searching for particular types of stars or even particular types of galaxies. We're looking for places that could have life. Now suppose for every ordinary star, no matter how many planets it had, one of those planets was capable of supporting life as we know it. So how many planets would be in the whole galaxy? 100 billion. And in the whole universe, there's about 50 to 100 billion galaxies. You take those two numbers and multiply them, that gives you the total number of ordinary stars. That's a 1 followed by 21 zeros. 1 sextillion. Most people, nearly everyone, has never had an occasion to greet that number, 1 sextillion. But let me give you an idea of how big it is. It's 100,000 times bigger than the total number of all the sounds ever uttered by all human beings who have ever lived. That's how big that number is. That's how many stars there are in the universe, and perhaps that's how many planets there are capable of supporting life. Unless, of course, we're unusual. That's an unpleasant thought. I'd like to think that we're common. But let's take a look to get a sense of how many stars there are. In this view, we have a tiny piece of the sky pointed towards the center of the Milky Way galaxy, in Sagittarius. Sagittarius gets the award for having the most stars in it because those are the stars that trace out the constellation Sagittarius are sitting in front of our sight line that goes straight to the center of the galaxy. And all these stars are crammed in there. That's just stars in one patch of sky in our own galaxy. Imagine summing that up for the whole galaxy and across the universe. So, dare we think that we're alone? Now, it turns out, to theorize about there being other worlds, other places where you might find life, to theorize about that wasn't always met with support or praise. In fact, in the year 1600, this brother Giordano Bruno, who's a monk, he lost his life. How did he do that? Well, it wasn't really his fault. In the Square of Flowers in Rome, the Catholic Church burned him naked at the stake. Naked at the stake. And had he just been an ordinary heretic, they would have just burned him without removing his clothes. But he was an impertinent and pertinacious heretic. Why? What was his crime? He suggested that the universe must be infinite because if it were not infinite, then it would have to be here instead of there. And how could it be in one place and not another? because if it's finite, it's leaving out some space over here. So his philosophical sensibility told him that the universe must be infinite, because it can't be one place and not another. Number one. Number two, from the vastness of this infinite universe, he concluded there must be many worlds beyond Earth just like Earth. And he was rather animate about this. This got him into deep trouble. Enough trouble for him to be burned at the stake. It was against Scripture, against Catholic interpretations of Scripture. In fact, there's a statue to him in the Square of Flowers in Rome. He's posed with his robe on. My last time in Rome, I had a pilgrimage to that statue, thinking to myself, they don't do that anymore, fortunately, because I'm talking about planets beyond Earth all the time. And not only is that work praised, but it sometimes makes headlines. So how do we find these planets? Well, it's a challenge. It's a challenge. You don't just look up and say, oh, there's a planet. It takes much more than that, because these planets are in orbit around a host star that's vastly greater in brightness than the planet itself. And so there's a challenge there. It's a challenge. You have to detect something that may be only 1/100 millionth the brightness of the host star. It'd be like, you know, catching a firefly and putting it in one of those beams, one of those Hollywood searchlight beams when there was a movie opening. Just toss the firefly into that beam, step back, and say, where's the firefly? Show me the light of the firefly. It's there, but you have to somehow block the rest of the light, eclipse it, occult it, somehow suppress it so that the light of the firefly can show up a little better. Now, it turns out many planets, as well as solar systems in formation, give off principally infrared light as opposed to visible light. All they do is reflect visible light, but they give off infrared on their own. And in fact, they are more brighter compared to the host star in the infrared than they are in the visible. So what you might be able to do is whip out an infrared, but tactics nonetheless. And in combination with that, in fact, we found a way. I don't know if you've ever seen a total solar eclipse. If you go see one, you're out there, the sun is there, the moon goes in front, and right when the moon fully covers it, the sky goes dark. Stars come out. You have blocked the light of the host star, enabling you to see things that are much dimmer, that were always there. You just didn't notice them before because things were too bright. We have figured out a way to, within the optics of the telescope, put an eclipsing disk in front of the host star, blocking out most of its light, enabling us to see whether there's any signature of a tiny bit of light nearby, possibly in orbit around the host star. You hope that, and that's not just some chance juxtaposition of another star in the background. That would just be bad luck. By this method, in fact, one of the first things discovered was one of these orbiting disks of a solar system in formation. And that was the star Vega, one of the brightest stars in the nighttime sky, visible throughout the evening sky in the summer, or very early morning hours, the wee hours of the morning in the winter. Vega goes right overhead at night for most residents of North America, and a close examination of that star revealed that there was sort of an infrared emission surrounding the star. And a closer analysis revealed it to be craggy chunks of rock and dust still in the act of forming a system of planets that we have come to take for granted that exist in our own solar system. Now, the Vega system, this fact about Vega was well known to the authors of the story Contact, you might remember the film where it chronicled our first encounter with extraterrestrial intelligence. Vega, the signals were coming from Vega. And the scientists, upon realizing this, said, they can't be coming from Vega. You can't have a civilization on Vega because there's still rocks trying to form a planet. If you don't have a planet, how are you going to have a civilization? So this was an argument to sort of wonder further how it was you would have signals coming from such a planet. And I was proud of the producers and the authors for having included late-breaking scientific news in the storyline of a science fiction film. Because they could have just made stuff up. It is science fiction, after all. But they didn't. They kept with the facts. And later on, it was revealed that the alien intelligent civilization evolved somewhere else and had an outpost on Vega. And so, just a little piece of fact about that. But we were all excited. This happened back in the 1980s when this disk of material was found around Vega. But again, you're not really rocks. You want planets. You want planets with stuff on them. And so, where should you look? There are a lot of stars out there. A lot of stars in our Sagittarius star field. You just start at one corner of the photo and just sort of work your way. Well, you can do a little better than that. You can do a little better. Because we know that the sun has planets. Why not look for other sun-like stars? And that way we'll look for life as we might expect it to be. Let's look for sun-like stars. And in that search, you better remove from the sample those stars that are in binary and triple and multiple star systems. And any night, if you go out with binoculars or even a modestly powered telescope and look up, half of the dots of light you see, when you zoom in on them, you'll see that they're actually 2 stars or 3 stars. And if you waited long enough, thousands of years or so, you'll see them in orbit around each other. These are multiple star systems. And it turns out planet orbits are not especially stable if they're trying to navigate their way around a changing gravitational field. Often they get jettisoned into into interstellar space. In fact, we expect the whole population of vagabond planets to be roaming the galaxy, having been jack-in-the-box jettisoned from their original star system. So you're not going to look to the multiple star systems. You want to get the single stars where they have stable orbits. And, maybe there are interesting planets around high-mass stars that are extremely luminous, or low-mass stars that are relatively cool and dim. Maybe, but I don't want to start my search there. I have limited research funds. I want to maximize my chance that I'm going to find what I'm looking for, because I know that we exist. We already have a test of concept. It's us. So later on we'll go back. We'll go back to the other stars. Once we're happy with looking for ourselves, then we could look for the weird cases. I don't have a problem with that. But first things first. First things first. Well, how do you find them? Is there a better way than squinting and blotting out the? Yeah, there are several ways. Well, one way recently been pioneered, because we didn't even really think it was possible. You have the host star, and let's say it's got its planetary system. Well, many views of that planetary system, you might have a bird's eye view. Birds don't fly in space, of course, so this one being figurative. Birds, they would just drop. There's no air. But so you have your view from the top, and there are a lot of views of the planetary system you might have, but one of them might be edge-on. There might be a system out there, and all the random configurations of their orbital plane, one of them might be edge-on. Edge-on. And if it's edge-on, and there's a nice big fat planet there, like a Jupiter, that Jupiter is going to swing around and move in front of the host star. It's not going to cover the whole star like a sun-moon eclipse, but it's going to block out some of the light of that star. And if that star has normally stable light output, and I'm monitoring its output, and all of a sudden I go, boop, boop, and that repeats at regular intervals, I've got an eclipse on my hand. I've got light being blocked from that host star by something that passes in front of it at regular intervals. I've got a planet. So planet eclipses is a major frontier that we now have because one of the easiest things to do is to check for the variation in light of an object that might otherwise be stable in its light output. Legions of amateur astronomers can help out this effort in their backyard. Now, what you hope is going on is that the planet, that the host star isn't very pockmarked. You may remember, or you heard, that the sun has these things called sunspots. They're spots on the sun. This is astrophysics. We call it as we see them, sunspots. We don't invent Greek and Latin names for these things. Sunspots. So the sun has sunspots. Sometimes it has more than other times. And so as they move in front of the sun, the luminosity, the radiant energy from the sun changes. So we have to be very careful that we're not measuring just some rotation of the sun carrying a blot, a dark region in front at regular intervals, and make sure we're not looking at that compared with the planet that would come in front of it blocking its light. And it's not an obvious answer about how you would protect against this being fooled. You know that a planet would eclipse at regular intervals basically forever, whereas sunspots come and go. So you're going to check for signatures that might disappear. So either the planet got eaten, or in fact, your false signature was sunspots. Another way to look is something called microlensing. This is a brilliant, high-tech. It taps some of the basic tenets of general relativity, Einstein's general theory of relativity, which asserts, and has been demonstrated to be true, that in the vicinity of a source of gravity, the fabric of space and time warps. And it doesn't matter how big the gravity is. It warps much more around high sources of gravity. The low sources of gravity warps just a little bit. Okay, now watch what happens. If there's a star in the distant part of the galaxy, and I have a planet, one of these vagabond planets, it wouldn't have to be a vagabond, but let's just say a vagabond planet. If that vagabond planet passes in front of the star is so far away, it's not going to actually block much of the light. It's just because it's all far away and the planet is just this infinitesimally small dot moving across the surface. That's not what we're measuring here. What we're measuring is, it turns out, that the gentle curvature of space around a planet is just enough so that the paths of light from different directions, below, to the side, and above, from this distant star, get bent just enough that they get focused. And so that as a planet drifts past your field of view, the starlight greatly increases in brightness. It spikes and then drops back down again. And we know exactly what that rise and what that fall should look like. And this is called gravitational microlensing. It's as though the planet's gravity served as a lens to focus the light of a distant star behind it. One challenge for this effort is, of course, it's a non-repeating thing. The planet just drifts by and keeps going on its way. Plus, the chances of a planet exactly crossing the view of a star, that, given the vast emptiness of space, you've got to monitor millions of stars and track and some stars change their own brightness according to their own habits. So you have to know what that change looks like versus what this change looks like. But it's called gravitational microlensing. And we're building a catalog of how many planets are out there floating through space simply because we see this effect of the light from a distant star. So that's another way to detect them. But again, you're not waving to aliens in this effort. You're just sort of identifying the fact that there are planets out there. And you want to do a little better than that. And in fact, we want to know, well, how much mass does the planet have? How big is it? Could it look like Earth? The most tried and true way that we have discovered planets, and the way that's responsible for all of the 100 planets that are now known outside of our solar system, uses a principle first discovered by Christian Johann Doppler. He did this back in the 19th century. He's a German physicist. And what he did was he did a very simple experiment. We've all noticed this. He noticed it with train whistles back when trains were more common than cars. But he noticed that a train that tweaked its whistle as it approached, the pitch of that whistle sounded different as the train approached than it did as it receded. The pitch changed. Now, either the conductor has got, a whole symphony of whistles and he's changing it just as he goes by you, or there's something more fundamental going on, because no matter where you are, you hear this. He's not doing this for your benefit. And trains really do only have one whistle. So they might have a few, but they don't have a symphony of them constantly changing frequency as they go by you. They have better things to worry about on the train. So the pitch goes, I can't imitate a train whistle. I'll imitate cars driving by swiftly at a racetrack. Same difference, because the tires make sound on the thing. Okay, ready? We know that sound. We've heard that sound before. Have you ever questioned it? Have you ever wondered, why does it sound different coming towards me if it goes away? Maybe you hadn't, because you just accept it as just what goes on in life. Hear it again. It doesn't go, it doesn't do that. It doesn't go, it doesn't do that either. Doppler measured that first in the 19th century. He didn't just simply assert that it was so. He found a mathematical form that described exactly the rate that frequency changes. And it's a basic property of waves. That happen to be sound waves emanating from an object in motion. But it also works for light waves. Light. And so how do we invoke this for stars? Well, here's a diagram. You've got a telescope, and it's looking towards a host star. And in this figure, you notice there are two sort of yellow suns there, but that's not a double star system. That's one sun moving around some dot in space. Now, what's going on there? Well, something I hadn't told you yet. If you're a star and you've got a planet in orbit around you, typically people think, oh, the star is in the center and planets go around the star. No, it's not what's happening. What's happening is the star and the planet orbit their common center of gravity, which generally is not at the center of the star. So if you can't see the orbiting planet because it's too dim, too far, too whatever, but you certainly see the light of the host star, and you monitor it, and you notice that it's got these Doppler shifts. Sometimes the light is coming towards you. Sometimes the object emitting the light is moving away from you, just like the train moving past. You can measure the change in the frequency of the light, which is also a change in its wavelength. The two go together. High frequency, low wavelength. So here's the star doing this in reaction to the fact that a planet is in orbit around it. But you not only could find one orbiting planet, you can find multiple planets this way. Because you look at the variation of the host star, and you say, okay, I've got this 12-year period in there. There must be a planet at 12 years. Oh, wait a minute. There's another level of jiggles on top of that 12-year jiggle. So the host star is not only reacting to one planet, it's reacting to another planet, combined. So you have to tease one from the other, find the two signatures, and then you get to report that some planets have multiple star systems. This is making evening news. This Doppler effect, we've seen this, maybe not with light, not with train whistles, because nobody hears trains anymore, but you've seen this fellow. We know him. We know his name. He's got the radar gun. In this case, he's using microwaves. Bet you know you're being beamed by what microwaves when you get your speeding ticket. It's a microwave gun, and using basically the same principle. And he can measure your speed if you're coming towards him or if you're moving away. It's just harder for him to catch up with you if you're receding. So he tries to get you as you're coming towards him. The old radar gun. Well, the first set of planets discovered by this method were Jupiter-sized. They were Jupiter-sized planets. massive. And that's kind of to be expected. The biggest signature that you're going to find the easiest data to acquire. And it's not going to be the tiny tug from a small Earth-sized planet. It's going to be a big tug from a big planet. So the first 50 planets, 60, 70 planets, were all Jupiter-sized planets in orbit around the host star. Not surprising. Not a problem. It's like looking for your car keys under a lamppost. That's the easiest place to find them, so you look there first. Okay, if they're not there, you look somewhere else, but if you find them there, you're doing good. But here's another problem. There's another problem, that the first set of these planets that were discovered, and I've got the list here, some of the first three, we have planets in orbit around the star 51 Pegasi, 47 Ursa Majoris, and 70 Virginis. There's a code for 51 Pegasi is the 51st brightest star in the constellation Pegasus. 47 Ursa Majoris, 47th brightest star in Ursa Major, a piece of which is better known as the Big Dipper. And 70 Virginis, the 70th brightest star in the constellation Virgo, Virgo the Virgin. Now these stars were had Jupiter-sized planets, not orbiting where our Jupiter is, but really close, up close, in a place that we never even imagined could be. We had to throw out all of our theories of planet formation because we only had one solar system. And we figured we must be representative, everybody else must look like us, and so our theories must produce a solar system that resembles us. Rocky planets in close, massive gaseous stars further out. None of them, thus far, look like our solar system. And that's puzzling. Is it our method that it prevents us from seeing? Maybe. We've only been doing this for about 10 years, 7, 8, 9 years, to find massive planets orbiting much farther away from their host star. They'll take anywhere between 8 to 20 years to go around their host star. So we don't even have a baseline yet to measure a full orbit of solar systems that might have a very distant massive planet. So the jury's still out, although it's still puzzling. It's got people wondering. As I said, we've got more than, we've got hundreds of these across the sky. We've got an artist rendition here's a double planet star system, just trying to imagine what it might look like. These are the times where you need artists because you feed them the raw data and they got to show you what it might look like for your dreams and for the next generation of science fiction films. But you add all these up, there's 100 of them across the sky. They're all over the sky. They're not just in one spot. They're everywhere, which is encouraging. Recognizing, of course, that planets are everywhere. But how do you get massive planets in close to the host star? This was a mystery for a while, but we have some clever theorists who noticed that if you're a massive planet and your solar system's still forming, there's a lot of debris between you and the host star, you can do kind of depending on the orbital dynamics, you can actually exchange places with material. Fling material out as you migrate closer. And in the act, you're sort of vacuuming out the interior of the solar system, exchanging momentum, angular momentum. And the act of doing that gets you closer to the host star, evacuating the area in the process. And this is part of the dynamics that enables planets to be flung to and fro, because the massive planets are wreaking havoc on the stability of the system. Well, you ever go want to visit these planets? They're far, even the closest ones. If we went 1,000 miles per second, imagine traveling that fast. That's 100 times faster than any human has ever traveled, ever. Let's go at that speed. It would take you 800 years to reach, 800 years to reach the closest star to the sun. And that one, we don't have any planets. You want to reach one that's got planets, it'll take you 2,000 years. So you'll be long dead before you got there. But you might still want to make a catalog of this in case one day we figure out how to do it. One rule of space travel is you want to get to your destination before you die of old age. This is a criterion. But you want to pick your planets carefully. There's a new plan for NASA to build what we call the Terrestrial Planet Finder, TPF, and combine that with another one, SIM, the Space Interferometry Mission. These are missions up in space that have a bank of telescope dishes working in harmony to give you the sharpest possible image of the smallest possible objects. We want to get an image of an Earth-like planet. We want to see the oceans. We want to see the texture. We want to measure the atmosphere. Whip out a spectrograph, then you can measure the chemistry of the atmosphere. Now you're talking, because the chemistry of the atmosphere is a product of what's going on the surface. We've got oxygen. We breathe it. But oxygen is a smoking gun of the fact that you have metabolism going on here on Earth. Without the metabolism, the oxygen would go away. It's unstable in anybody's atmosphere. Methane is unstable in the presence of oxygen. We've got methane around because it's got a constant source from farm animals, among others. Ozone. These are signatures that if we find on another star, if I'm going to pick them in order of which one I'm going to visit, there you go. I've got them. That's where I'm going to go first. You know, our spectrographs might also detect chlorofluorocarbons, ozone-destroying chemicals. It might find hydrocarbon contaminants or soot from global deforestation. Suppose it finds that. Well, that would be a sure sign that on that planet there's not a single sign of intelligent life.